Hi everyone, welcome back to section 6.1. And in this 6.1 video, we're going to be reviewing another topic from Calculus 2, and that's going to be Taylor and Maclaurin series, and most notably Maclaurin series, okay? So before that, let's kind of define what analytic means. So a function is said to be analytic at a point A. We'll be talking about analytic quite a bit in this chapter, but here's really our first instance if you haven't seen it before. It can be represented by a power series x minus a with either a positive or an infinite radius of convergence. So what does that mean? In calculus, it is seen that infinitely differentiable functions like exponential, trig, logarithmic can be represented by Taylor series or Maclaurin series. So here are some well-known Taylor series, but when we have a center of A equals 0, okay, when we have a center of 0, that means we have a Maclaurin series. Okay, so you've seen quite a few of these before in Calculus 2, hopefully, as Maclaurin series are a learning requirement. But here's some well-known ones that we typically establish in Calc 2 by doing it by hand, and then we have them moving forward. But here there is a table right here. So these are integral convergence and the series. And what I typically like to do is also state what the radius of convergence is as well. Okay, so radius of convergence. We like to include that as well. So this would be, we're going from negative infinity to infinity, so the radius would just be half of that. So it's just infinity. Same thing for the cosine and sine. For inverse tangent, our radius, our interval convergence is -1 to 1, so our interval radius of convergence would just be 1. But then for cosh and sinh, it would just be infinity as well. Same thing for natural log, 1 and then 1. Okay, so just a little bit of background for Maclaurin series. So one thing just to practice a little bit, refamiliarize ourselves a bit, is try to manipulate some of these. So, we can change the above series to have any input, not just x. So if we have cosine of 5x squared plus 1, we could use, we're right here, we can use this and just input in 5x squared plus 1. So this could be the series n equals 0 to infinity, -1 to the n, over 2n factorial. And I'm inputting in that 5x squared plus 1 in for this x. I'm plugging it in right there because that's our input. So this would be 5x squared plus 1 to the 2n. Okay, and if I wanted to write out a couple terms of this, like why not? I'm just going to plug in n equals 0, n equals 1, n equals 2, n equals 3, etc. So this would be like 1 minus 5x squared plus 1 squared all over 2 factorial plus 5x squared plus 1 to the fourth all over 4 factorial minus 5x squared plus 1 to the sixth all over 6 factorial plus dot dot dot. And I could get these by plugging in the n values, or I can see, what is giving me right here in these first couple terms. I'm just plugging in 5x squared plus 1 in for x. And so we could try another one. Doesn't even have to be an x. It could just be like a smiley face, e to the smiley face. So what we can say is, n equals 0 to infinity, um, smiley face. Maybe I'll circle it. That's raised to the n over n factorial. And where am I getting that from? I'm getting it from right here. Okay. And I'm just plugging in the smiley face in for x. So what this would be is 1 plus smiley face over 1 factorial plus smiley face squared over 2 factorial plus smiley face cubed over 3 factorial dot dot dot. Okay, so that's us manipulating Maclaurin series a bit, right? Just we have these well-known Maclaurin series, and based on the input or multiplication, we can rearrange and make a new type of series based on these definitions. But that's it for this video, just reintroducing Maclaurin series, which is a Taylor series that is centered at 0. But thank you for watching, and I'll see you in the next video. Take care.